This preview is for evaluation only and cannot be used for public screening.
On clear nights, a magnificent starry sky stretches above us. It moves us. It amazes us. It keeps its secrets. Secrets waiting to be discovered. Four centuries ago, something happened that was to change everything. It opened a new window on the universe.
Mio Dio, che cosa vede qui? Questo non può essere vero. Il cielo è stato maledetto.
Signor Galileo, we need to discuss something very important.
Buongiorno, dear friend. Venga, what is it? Come in.
This book here, Astronomia Nova, I just got hold of it. This Johannes Kepler, the astronomer from Prague, he openly proclaims that the Earth revolves around the sun.
My friend, as you know, I share Kepler's views.
Come, sir, I beg you, be reasonable. Earth is the center of the universe. Kepler's theory has no basis.
Not so, my friend. No longer. Look here. This is the instrument with which I can prove it. Come here. Look at it.
Is it a telescope?
Yes, yes, of course. Truly a technological marvel, a miracolo. What is far away suddenly seems quite near. Venite, caro amigo. Look up above you. There is the moon as you've always known it. And now? Now look through the telescope. Don't be afraid. Have a look and see for yourself.
What's that supposed to be?
That is the moon.
That's the moon?
Look closely. Do you see the mountains, the valleys, on the moon?
But we've known for thousands of years that the moon is a perfectly smooth sphere.
You've seen it for yourself. We got it wrong. Things in the heavens are not perfect. They are just as they are on Earth. Allow me further evidence. Over there lies Saturn. We see only a bright star. And now, look through the telescope.
What is it? I see nothing but a hazy blur.
What you see is Saturn.
But why such a peculiar shape?
That's something I'd like to know too. The great Aristotle taught us that everything in space is perfect. But I think that he and all the other philosophers after him were mistaken.
Galileo, how can you say that?
Yes, they were all simply wrong. Because they could not see what you and I have seen. There's more. One further proof. Let's look at Jupiter. I'll focus the telescope on it. Look.
Jupiter. A majestic planet. But tell me, what are those tiny lights?
There are small stars around Jupiter. I've been watching them for weeks. They move. They circle around the planet. And I tell you, friend, that Jupiter is its own orbital center.
No, that's nonsense. Quite wrong. The Earth is the center of the universe. All things circle it, as the theologians teach.
Yes, I know, but they have no proof for their teaching. What is in your book? In that book by Kepler, that can be proved. Come here.
This preview is
Another
for
proof.
evaluation only and cannot be
Milky
used
Way.
for public screening.
It's breathtaking. This shimmering band spread over the whole night sky. A puzzle throughout history. And now, peer through the telescope.
Galileo, you're playing a trick on me. Where is the Milky Way? I can't see anything.
Oh yes, you see it very well. What you have known as a shimmering cloud is in fact myriads of stars, countless solitary stars.
Absolutely impossible. It can't be true.
You've seen it for yourself.
Yes, but are you quite sure? Does this prove anything? This instrument could deceive us. Scholars can't have been wrong for thousands of years.
Oh yes, my friend. This instrument proves it, and it'll change the world. It opens a new window to the skies, and we can see what no man ever has. The universe, with all its secrets, is waiting for us to discover it. We just have to look hard, to observe accurately, to study the universe carefully to understand our own world.
All stations OD on the OD loop. In 10 seconds, we'll start the roll call for the Herschel and Planck launch. Herschel song.
Herschel song, go.
Planck song.
Planck song, go.
Herschel data.
Herschel data, go.
Planck data.
Planck data, go.
Herschel power.
Herschel power, go.
Planck power.
Planck power, go.
Herschel spacon.
Herschel spacon, go.
Planck spacon.
Planck spacon, go.
OM.
OM, go.
Softchord.
Softchord, go.
Flight dynamics.
Flight dynamics, go.
That completes the roll call.
This
for the Herschel
preview
Planck
is for
launch. We're ready to
evaluation
go.
only and cannot be used for public screening.
Allumage des Vulcains. Allumage des EAP, décollage.
That all went well. Dead on schedule. The launch vehicle's right on course.
You guys look pretty tense. And for me, it's always exciting to be part of the launch atmosphere.
Did you get some good shots?
Yeah, very happy. And you too, huh?
Yes, but for us, the tension isn't over yet. Our part of the mission won't start for another half hour.
Oh, you mean the moment of separation of the satellites from the rocket?
Yes, exactly. That's when the control room gets down to serious work. Because the space telescopes are entirely in our hands.
Michelle, can I ask a stupid question?
You know, I don't think stupid questions exist. Go ahead.
Why all this enormous effort? State-of-the-art technology? Telescopes of these dimensions? Huge rockets fired into space? I mean, we have telescopes here on Earth.
Well, I can explain that. Come with me. For 400 years, we've been improving telescopes, making them more and more efficient. Their mirrors have diameters 100 times larger than the lenses of Galileo's telescope. They capture 100,000 times more light. They can obtain images of outer space that would have left Galileo and Kepler breathless. Look here. This inconspicuous nebula spot emerges as a giant gas cloud. It's the remnant of a star explosion that was recorded 1,000 years ago. Because of its shape, we call it the Crab Nebula. And this cloud has been named the Eagle Nebula. With the very large telescopes of today, we can see newborn stars blinking out of those pillar-shaped objects. The Milky Way appears to us in the night sky like a broad band of countless stars. But in fact,
This
it's a
preview
giant
is for
spiral
evaluation
formed by the
only
stars.
and cannot be used for public
This
screening.
is a remote Milky Way. It looks similar to what our own Milky Way looks like if we were to see it from outside our galaxy. In this picture, you can see that Milky Ways do not consist only of stars. They are framed by dark clouds, clouds consisting of gas and dust. Telescopes on Earth cannot see all these details well enough. They can capture only a small amount of the radiation that is emitted by celestial bodies. That's why we're sending telescopes into space. Telescopes which allow us to register the full radiation spectrum and explore the complete cosmos.
What kind of radiation are you talking about?
We could say it's invisible light. Like visible light, it ripples out in waves. And all the colors of the rainbow have their own wavelengths as well. That's the distance from one wave crest to the next. With visible light, red has the longest wavelength, and violet the shortest wavelength. It's the same with invisible light. The different wavelengths just go beyond violet and red. And the whole range is called the electromagnetic spectrum. The largest part of the electromagnetic spectrum when it meets Earth's atmosphere is fully absorbed or strongly filtered. And that's why we send telescopes into space. They observe the wider range of wavelength. Every telescope reveals to us its own window to the universe. High-energy radiation has shorter wavelengths, shorter than the violet light that we can see. Ultraviolet radiation, for instance, is high in energy. That's painfully clear when we get sunburned. And of course, you know, the famous Hubble Space Telescope examining the cosmic UV radiation emitted from bright young stars.
But UV radiation penetrates through the atmosphere. So why do we need space telescopes?
Only a small fraction gets through. And with shorter wavelengths, there's nothing at all. For instance, X-rays. I think we'd agree that we're fortunate. Our atmosphere shields us. Non-stop X-rays aren't a good idea.
So how do you detect X-ray radiation?
Space telescopes have sensors that deliver streams of data depending on the wavelengths they detect. These create an image of the radiation, but this is just a pattern. We add the colors that we can see. This picture shows the remnants of a star explosion. We've given a blue color to the shorter wave X-ray radiation, and the longer wave X-ray radiation is a reddish yellow.
What about radiation with even shorter wavelengths?
At the end of the scale is gamma radiation, extremely rich in energy. The first gamma telescopes revealed something extraordinary. Light flashing everywhere in the cosmos. This was a revelation. These flashes result from violent supernova explosions. With gamma light, the Space Telescope Integral can observe the end of superstars' lives.
And the satellites that have just been launched, that's Herschel and Planck, what do they observe?
Unlike Integral, they'll examine the long section of the spectrum.
The wrong section?
Not the wrong end, the long end.
I see.
Where the electromagnetic waves are longer than visible red light, infrared, then microwaves, radio waves. Herschel is a telescope to detect infrared that you can't see, but experience as heat. Up in space, you commonly find infrared, where stars and planets evolve. And with this infrared telescope, it's possible to look into cosmic dust clouds.
That sounds almost mystical. And I see scientists as so prosaic. You've got to agree.
This
Your
preview is
satellites
for
don't really have
evaluation
very
only
imaginative names.
and cannot be
But our
used
names
for
aren't that
public
creative.
screening.
Very boring. There are satellites called P3E or TD1A. But that's not true of the technical marvel that we just shot into space with the Ariane rocket. Here we had a great inspiration for the name. William Herschel, who discovered infrared light. The Herschel telescope collects infrared light from space with the largest mirror ever placed in orbit. Up till now, infrared images have been rather blurry. But with this fantastic mirror, we will obtain images we could only dream of before.
This satellite is enormous. Amazing that it can actually lift off.
Yes, the scale is remarkable. Almost 8 meters high and more than 3 tons in weight. It barely fits into an Ariane rocket. Everything, each single screw, every cable, is tailor-made. Tens of thousands of man-hours. It was built in Europe and then prepared for launch at the Technology Center of the European Space Agency in this totally dust-free environment. You've seen that the launch process is quite violent. Satellites have to resist that, so they are agitated on a vibrator plate for several days. Then they go into a vacuum chamber where the vacuum of outer space is simulated. The satellite has to withstand the vacuum and the sudden extremes of heat and cold. The point is, it has to work faultlessly.
That's a lot of effort to get better pictures. And what are these pictures Herschel will shoot?
One interesting object is here, for example, in the Orion cloud. A striking constellation you can see with the naked eye, especially in winter. In ancient Greek myth, Orion was a great hunter, but a tragic hero as well, who continually chased the lovely Pleiades, but could never catch them in the sky. These 3 bright stars form Orion's belt. 2 stars on top mark his shoulders, and 2 at the bottom his legs. And look there. Below the belt you can see a small nebula spot with the naked eye. By using a telescope, you see that this tiny spot is a glowing gas cloud that is illuminated by bright stars. And this is where it becomes really interesting, because inside this bright area of gas are dark molecular clouds, and we can look into these clouds with an infrared telescope. And what we see here, Sven, is something astounding. It is the birth process of stars. This is where new stars are being born.
Why do stars form here in particular?
The clouds of hydrogen molecules here are the densest and coldest. So a process starts in this region, a process of no return, in which these cold clouds implode under their own weight. A slight impetus from outside is enough, and the breakdown begins. If the explosion of a supernova near such a dark cloud gives the cloud a kick, it starts to collapse, and then there's no stopping it. Deep inside the cloud, cores are steadily growing and collapsing. This sequence heats everything up. In the beginning, just a few hundred degrees, not even lukewarm for a star. But for an infrared telescope, this is warm enough to see these so-called protostars through clouds. Little by little, the protostars heat up to some 1,000,000 degrees. And when finally the nuclear fusion ignites, a new star is born. A dazzling sun.
Okay, so cold gas turns into a hot core, and finally into a star.
And not only new stars are formed, but also new planets. They form from the gas and dust left over that's orbiting around the protostar. We know that every new star is surrounded by a dust ring.
This preview
but
is
not
for
every new star
evaluation
forms
only
new planets.
and cannot be used for public screening.
In the Orion Nebula, for example, the new stars seem to be blowing away their dust rings much too fast. Probably too fast to let any new planet be formed. Of course, we would like to watch this process, and that's why we need the sharper infrared images from the Herschel spacecraft. We'll be able to see the rotating dust shield and forecast how long it'll survive. There must be a critical point, but we have to find it.
Sounds really fascinating. Were our planets and sun formed like that?
That's what we assume, but we can't observe it naturally. That's why we look around the universe to find some answers to how things work.
How long will a new star live then?
Well, till it dies.
Really?
They're all quite different. There aren't any rules. Millions or billions of years, let's say. Just look up there, Sven. You see that bright, light red star?
Mm-hmm.
There are lots of those. And that one's called Arcturus, in the Boots constellation. Arcturus is found easily enough via the Big Dipper. The Big Dipper consists of 7 stars. 3 of them make the handle, and 4 the bowl. Follow the curve at the end of the handle stars, and there's Arcturus. Arcturus is a red giant. That's a star having used up almost all its fuel, so is approaching the end of its life. At this stage, the nuclear fusion moves to the outer layers, and the star expands to become a red giant. The star exterior cools off and becomes red, giving it its name, red giant. And as its end approaches, it starts ejecting large parts of its mantle into space. Giant masses of gas and dust are projected, ready to form new stars someday.
So it's a kind of never-ending story. The gas and dust clouds become stars, and the stars turn into clouds, and so on and so on.
Exactly. Stardust forms new stars and planets. And this is probably how our Earth was created, too. Everything you see, your camera, your jacket, and the matter we are made of, everything is part of this cosmic cycle.
But there must have been a first moment sometime.
Yes.
How did it all get started?
That's the question the Planck telescope will answer. It's the second satellite that we just launched. It will observe the oldest light in the universe.
Ah, the Big Bang.
Not exactly. The Big Bang was, it was actually invisible. In the first, say, 400,000 years after the Big Bang, space was full of hot matter. A very, very strange situation. A blazing, hot mixture of exotic particles. In this particle soup, everything was forever changing. And it was so dense that even light was captured within it. Only when this mixture started cooling did the universe become transparent. Light could travel unimpeded through space. And since then, it has been racing throughout the universe.
So it is the oldest light in the universe.
Yes, the first light. This ancient radiation, which is called cosmic background radiation, because it comes from all parts of the universe at the same time. It's a bit like cosmic wallpaper, lining all the visible universe. The Planck telescope slowly revolves on its axis, mapping the entire cosmos, stripe by stripe, point by point.
This preview is for evaluation only and cannot be used for public screening.
It takes 6 months to get one complete picture of the cosmic microwave background.
Hold on. What do you mean, microwave? Didn't you say it was light from hot gas? And that should be visible.
Yes, well spotted. But since the Big Bang, light itself has transformed. The original light of the universe does indeed come from the hot particle soup, and that was rather shortwave. But then the universe itself expanded, and the original light was stretched. The light waves expanded. They became longer, so long that they became invisible to us. So let's say that the original light was red, and then due to the expansion, it became infrared, and finally became microwave radiation, as it is today.
That's not easy to imagine, Michel.
Yes, I know. These processes are really complicated. But a great deal can happen in billions of years. We're even more interested in what's behind the cosmic wallpaper.
You mean behind the background radiation?
Yes. Or more precisely, I mean what's behind it in terms of time. What happened when the light was still captured in the particle soup of which we cannot see anything? Do you see those blobs on the picture?
Those colored patterns in the cosmic wallpaper?
Exactly. Those spots aren't there at random. They indicate some early parts of the universe being a bit hotter and others a bit colder. And from these small differences, we will deduce what the cosmos in its first hidden moments was made of and how it worked. Enough talk. Our world wasn't created in a day. How can you then grasp it in a day? We should go back to the control room. Only a few minutes until both the satellites separate from the launch rocket.
It's really fascinating. Your passionate enthusiasm for all the invisible unknowns. For me, it's as though I can actually see these things. The hot particle soup, the infrared rays, all the newly born stars. What a turn-on that is.
Listen, Sven. Science is the most exciting mistress there is. Once she's got you, she never lets you go again.
All stations, OD on the OD loop. Separation expected in a few seconds.
Well, I think the satellites are about to separate from the rocket.
ARS reports nominal separation.
Now it's the moment of truth for all of us here. See that line there?
Yes.
It monitors radio contact between the satellites in space and the ground station in Australia. If that line activates, it's all okay, and the mission can go ahead.
AOS expected in 5 seconds.
That's Herschel. Planck should follow.
This preview is for evaluation only and cannot be used for public screening.
What a moment. Thank you for letting me share it.
OM confirms acquisition of signals from Herschel and Planck at Perth.
Herschel Son confirms good telemetry from NNO.
Planck confirms good telemetry too. We just started checks on spacecraft status.
Tell me, what happens next?
Now we get down to work. First, the tests. There are the remote control procedures, attitude control, battery status, function of solar cells, the checklist, on the support systems, all the rest. That'll take some days, and then the satellites will journey through space for 3 months to reach their station, which is called Lagrange point L2.
And the telescope couldn't be closer to the stars?
No. With today's technology, that's simply not possible. The distances in space are much too great. I don't believe we'll even make it to our nearest neighboring star, called Proxima Centauri. Even a mission to our neighbor planet, Mars, is a giant effort. And Mars is really not that far away from us.
Do you mean you won't ever find out more about stars and galaxies? For example, is there something like life somewhere out there in the universe?
I don't think that we'll see extraterrestrial life through space telescopes. If we want to find life, we'll have to go there and look. For example, on the surface of Mars. By the way, do you know Anya Phillips?
She's due to be the first woman on Mars, isn't she?
Is she? Well, perhaps. A manned or womaned flight to Mars is incredibly challenging and vastly complex. It could be 20 or 30 years ahead. But Anya's working on a robot that's going to search for signs of life there. Drop in on her. It's very interesting.
Okay, thanks. I'll do it right now. So, Michelle, thanks for seeing me, and good luck with both the telescopes. And I'll be back in 3 months for the first images.
They'll be here. See you then.
Miss Phillips?
Yes?
Michelle sent me here.
Oh, hello.
Is this the new Mars robot? I imagine he would be smaller than that. And you built him?
Well, not alone. It's a project with 17 European countries and hundreds of experts. It's a bit like the motor industry. The chassis comes from England, the wheels are from Germany, instruments from all over Europe. My job at ESA is to make sure all the bits fit together. And do call me Anya.
Sven. Can your robot drive a little faster?
Yes, sure, but what for? Mars is an unknown world. Every centimeter is new and exciting. We want to examine everything, and snail's pace is just right for that. Besides which, we can't steer the vehicle directly. Do you mind? Take that a second.
Why can't you steer? What stops you?
It's simply a matter of distance. Mars is so very far away, but depending on its actual position, radio signals take 7 to 20 minutes to get there. So, let's say the robot detects an obstacle and sends us a picture down to Earth. We get it some minutes later and send "turn sharp right." Back goes the signal.
This
it's all taken
preview
too
is
long
for
an effective
evaluation
avoidance
only
maneuver.
and cannot be used
So all we
for
set is a
public
general
screening.
direction and schedule, and he has to cope with the details. He scans his surroundings and considers options. His cameras work like eyes, and then his central computer generates a 3D model. The environment and his route. The thing is, the steering will be automatic, avoiding cliffs, large boulders, quicksands.
And running away from the Martians.
Huh, right. The mission doesn't exclude that possibility. In the past, people thought up all sorts of crazy ideas about life forms that might exist on Mars. Today, we're in a position to find out with Mars rovers and satellites like Mars Express. With Mars Express orbiting the red planet, we have proved for the first time that water has existed on Mars in large quantities. Today, it's in the form of ice. This is very important because as far as we know, the evolution of life is impossible without water. Today, we are certain that a long time ago, Mars was a good place for life to develop, probably in a great ocean.
And what happened to it? To the ocean?
We don't know for sure, but a major part of the water is probably still there. Perhaps underground.
And if once there was life, it has dried up as well?
Yes, that is one theory. It's quite possible that simple life forms could have somehow survived in the Martian soil till today. And if they exist, count on it. Our last word in technology, our clever little robot, will show they're there. And if they do, even the tiniest trace, that would be truly sensational. Because it would demonstrate that life in the universe is a perfectly normal thing. If we find life there, we can assume that countless planets in the universe are swarming with life forms as well, and that there are billions of planets, Sven. They're countless.
Yes, I agree. That's exciting. When will it get going, your mission to Mars?
Not for a while yet. Not till 2016 at the very earliest. And after the launch, there's an 11-month journey till things get going. Up on Mars. At a snail's pace.
Wouldn't you really love to go, huh?
And how? But humans on Mars? That's for the next generation. Our job today is to check out the terrain with the help of satellites and robots, to find landing sites, discover water, identify dangers, and so on. But our children won't only be there to see it, they'll even be able to set foot on Mars. That's how science works. One thing is built on another. The work of thousands of scientists from past centuries is our scientific foundation today. And we go forward, step by step, observation by observation, adding new evidence. You know, Sven, for me, that's the real thrill of science.
This preview is for evaluation only and cannot be used for public screening.
New discoveries, new observations, they form our perception of the universe. Today, we can look deep into outer space with space telescopes, and satellites help us to explore our own solar system. And everything we discover will be new building blocks for future generations. The starry sky is full of secrets. Whether we ever understand them is up to us.